In this video, we're going to use the results from previous videos in this series to produce a parametric plot of the motion of a free particle of unit mass in the equatorial plane of a Kerr black hole using a Mathematica notebook, which can be found at the link here. So this is freely available on the web. What will be important though is that we'll have to modify this notebook because it was written for the Schwarzschild geodesics in the equatorial plane. So we're going to have to modify it for the Kerr black hole case. Before going to the notebook, I'd just like to run through some of the mathematics involved in altering the notebook and some of the physics involved and why it's necessary to change that. And then I'll briefly look at the notebook itself. But in part 2, the next video after this, I'll focus entirely just on this modified notebook. Okay. Now, so in the previous video, we found the equation that governs the motion of a particle in the equatorial plane of a rotating black hole to be this. Okay, this was the equation. We had R dot, and anyway, manipulating that, we have the kinetic energy part, a potential energy-like term called an effective potential. It's not actual. We don't have potential energy in general relativity. And then the energy term on the end, the energy of the orbit. So this particle will follow a particular orbit, particular geodesic, in the vicinity of this source mass m, capital M. The particle's mass is small m, and it's governed by this energy equation here. Kinetic part, effective potential part, which acts like a potential energy but is not, and the energy of the orbit here. Now, the effective potential Vf is this object here. Okay, h is the angular momentum of the particle of mass m, and it's just in the equatorial plane. So we're talking about the angular momentum around the axis of rotation, around the vertical axis of rotation. Okay, this motion here for this particle is restricted to the equatorial plane, nowhere else. So the polar momentum in the polar angular direction is 0. It's fixed at pi on 2, theta is pi on 2. We're in the equatorial plane only. Small m is the mass of the object. Epsilon is an energy parameter I'll get to in a moment. G is Newton's gravitational constant. A is the spin parameter of the black hole itself. Okay, and we'll actually be using the dimensionless spin parameter in here. C is the speed of light, and so on. All right, now the total energy of the particle E is a half mc squared epsilon squared minus 1. And the epsilon was, as in previous videos, it was E over mc squared. So it was a ratio between the energy at any point in the orbit to its energy far from the source mass measured by an observer at rest with respect to the particle m. So we can rearrange this. We're going to need to rearrange this because I want to solve for epsilon to substitute in here. And we're going to alter this slightly before we get to the Mathematica notebook. So we've got 2e on mc squared is epsilon squared minus 1. And epsilon becomes this object here. What we're going to do is substitute that into this effective potential term here, and then we'll use that new effective potential in the notebook itself. All right. You can see there's already here, there's a half, the 2 underneath. There's a c squared epsilon squared minus 1. So you can see there's an E term already there, an energy term, energy of the orbit. All right, so this leads to the following form of the effective potential. Here it is. Start again, and we'll just substitute in those terms we were rearranged or transposed to give us, notice here that the 2, the c squared epsilon squared minus 1 in parentheses is this object here, and that's just replaced by E. The epsilon over here, the object we solved for earlier on the previous slide, goes in here. Okay, so here's our new effective potential, and we will put that into the Mathematica notebook. Again, can I just remind you, the energy of the particle of mass m is E is minus p dot u. So p is the momentum of the mass m, and u is some observer. And we can imagine some stationary observer somewhere is being passed by the particle of mass m with momentum p. And so we can find the energy as measured by that observer at the location of the observer by the observer for this particle mass m that has this form momentum. So minus p dot u, the negative because of the particular sign of the metric I use on this channel, which is the minus plus plus plus. And so minus p alpha u alpha, that's the scalar form. Okay, when you do the contraction here, the inner product, we get minus m. Here is the form momentum of the particle, indices lowered, and here is the fall velocity observer at rest. Only the time component is non-zero, and multiplying that through, only the time components multiplied together, everything else is zero, gamma mc squared. So the total energy of the particle measured by the observer, the stationary observer U, is gamma mc squared, and that implies that the kinetic energy then is, this is the total energy, so we then subtract from it the energy at rest, we get ourselves the kinetic energy, the difference between these two. So this is gamma mc squared is the energy of the particle in motion as measured by the stationary observer, okay, but it's kinetic, the kinetic part of that is gamma mc squared minus mc squared, which is the energy in the rest frame. Mc squared is the energy in the rest frame. All right, the types of orbits can be categorized as E is less than zero, bound orbits. E equals zero, just that point between bound and unbound. Epsilon is 1. In that case, epsilon is 1 to give us E is 0. So that implies then that gamma must be 1, which means that the observer is at rest with respect to the object, so the kinetic energy is 0 at that point. E is greater than 0, we have unbound orbits. Greater than 0 unbound orbits. Now, in order to plot the geodesics followed by our particle in the equatorial plane, we need to find the form of phi of r. We want the azimuthal angle phi as a function of r. So we can do this using its derivative, phi dot of r, which we get from d phi d tau times d tau dr. That's from the chain rule. Okay, and we noticed that from the energy equation earlier, the total energy of the orbit, we had the kinetic part, the effective potential part, and the total energy. We've got a half m dr d tau all squared plus vf is E. Okay, and we can see we already have dr d tau, which is the reciprocal of d tau dr. Okay, and then we'll in the next few slides produce a form for d phi dr. Okay, so starting with that, with the energy equation before, energy in inverted commas, so to speak. A half m dr d tau all squared plus vf is E. Okay, let's rearrange that. So take vf onto the other side, subtract from both sides, then take the square root of it. Okay, also multiply, which gives us square root m on square root 2 dr d tau. Multiply by the reciprocal of those, root 2 on root m, and we have plus or minus this. Okay, now take the reciprocal, because we're going to use the chain rule later on. So d tau dr is this object here. Okay, so we're on our way. Now, next we need to remember that we have a killing vector in this geometry. K is k phi, e phi, and k phi is 1. It's here. We have in the phi direction, that's the angular part, around the vertical axis, the azimuthal angle. We have a killing vector in that direction there, a conserved quantity. As we found that the angular momentum is conserved in this direction. Only this component of the angular momentum, not the total angular momentum. Only the angular momentum around the rotation axis. Okay, in the phi direction is conserved, not the total one, not the one involving the polar angle and all the rest. Okay. Anyway, so from the conservation of the killing vector, we have d tau k dot p. It's the killing vector k. This is the form momentum of the particle. So we have d tau g phi phi, k phi, p phi. Okay, we contract k phi is just 1, so that drops out. So we have g phi phi times p phi, upper index there. Now the metric term here, g, lowers this p to give us the covariant form, the 1 form, p lower phi. And we know this is 0 because it's a conserved quantity. So the form momentum in this direction is conserved, okay, which means that first integral of this gives us p phi is h. Now p phi equals h is a quantity we found in a previous video. in the video 1 and 2 of this series. So we have an equation to describe that. And that equation is this. Now the thing is, we're interested in phi dot, remember, because we want to find phi as a function of r. So we're going to use the derivative of phi, which is phi dot. But we've also got this t dot here, and we don't want that. We just want phi dot on its own. So we're going to need to eliminate that. But fortunately for us, there was a second equation found in the first two series, and that concerned the energy of the particle. So we only need phi dot, not ct dot, so we can use another equation found earlier, which was also in the first video, and that was this one here in relation to the negative of the energy. So let's rearrange that, okay, to get ct dot by itself. Okay, so let's take this bit on the right here over the other side, give us this. Now let's multiply through by 2 on m to get rid of that, and multiply by g minus tt. Okay, and when we do that, we end up with ct dot is all of this here. All right, and then what we'll do is we'll substitute that back into p phi up here, and by substituting this expression for ct dot, we can derive an equation that contains only phi dot, which we can then integrate to give us the form of the geodesic phi of r in the equatorial plane, and that's what we're after, and that's the thing we'll plot in Mathematica. All right, so p lowercase phi, the one form p subscript phi is this. Okay, put that in there. Now, I'll warn you before I go further, the point of all this is I'm going to make some assumptions here. I'm going to make some approximations. There's a couple of them to produce a final form of the effective potential, and that's what the next couple of slides are about. So let's put that in there. Okay, multiply through. Okay, now let's evaluate the terms in here. Just remember, so GTT inverse is this object here. It's negative. Okay, and g phi t is negative. When we substitute all these, we end up with negative here, plus all these, substituting in g phi phi. It's this object, no it's not. Where is it? Yes it is. G phi phi is there. And what have I got here? I've got g phi t is this one, gtt is that one, yep. G phi t is that one, there's two of them squared, and gtt, sorry, my fault, is gtt, uppercase tt, all right, in there, plus this n term here, which I'll evaluate later, but I'll just leave for the moment. Let's just have a look for these. When we do a little bit of algebra, let's get some common denominators happening here, all right, across here, for instance. Sorry, where the one on delta is, and the one on delta is here. So let's put those in and get a common denominator. Okay, evaluate those. Now, when we do that, we've got this times this, plus, remember this one squared, that one and that one. Okay, now, next thing here, next line down is here in the this part here, we're going to get a common denominator again. So c squared r all across the bottom here, which means we'll have a c squared r cubed here, c squared a squared r here, and so on, okay? And then what we notice is, if you look here, this is r cubed r squared r, but we can see they're roughly of the same order. This numerator here is roughly the same magnitude, certainly the same order, r cubed, it's the highest leading term, roughly the same order. So what we're going to do, and the same in the second term here, what we're going to do is our assumption on the next page is that, and here we are again, r cubed is the leading term, r cubed, okay, but roughly the same order. There's an r there and r here. Use this extra r squared, but that minus in front. What we're going to say is that divided by that divided by that is approximately 1. So we're actually putting them together like this, okay, and we'll say that it's approximately 1. Okay, it's an approximation we're going to make, which will simplify our expression, but it still plots well, as you'll see later. Okay, so we get minus 2gm on c squared times e on r. We get over here, this is 1, so we get m on 2 gm squared on c squared r squared phi dot, plus m on 2 g phi phi dot. Okay, and what we're also going to do is make a second approximation and say that when we're plotting all our units in the Mathematica notebook, when we get to it, will be 1. So G, M, M, both M's, C, G will be 1, and we'll be plotting then the angular momentum, looking at the angular momentum per unit mass and so on in our effective potential. So the values of E tend to be small, whereas the values of R tend to be, the values of E, as you'll see in the notebook, tend to be less than 1, well less than 1, and this one tends to be well greater than 2, so it's an approximation. We can say this is very small, okay, but it's an approximation. You'll see that it works, but okay, so we're now left with, we've lost that first term now. We're taking that as setting that to 0, okay, approximate 0. And so we're left now with the second and third term here. All right, let's move on to that. So now we have that second term and the third term, and we know that's equal to h, or approximately h because of the approximations we've made. Okay, let's factor out phi dot here. Okay, so, and multiply through by 2 on m to get our m, and so we get approximate, so we get phi dot times this object is approximately 2 on m times h. Okay, then let's go for a common denominator as well here. Okay, and then what we're going to do here with our, we're then going to invert it so that we have phi by itself on the left, and that's approximately c squared on r squared over, so the numerator is c squared r squared over this object here times 2h on m. Okay, and what we're going to do is we're going to say that this is approximately equal to c squared r squared over this part here. We're going to say that r squared multiplied by this is much larger than this, especially when we set the units g and m to 1. We'll see that this r squared here and this term here, this metric term g phi phi, together are much larger than this object here. So as another approximation, our third approximation, we can say that c squared r squared on this 2h. Okay, so this object is approximately this. And then, of course, c squared r squareds cancel. So we're left with 2h on m times g phi phi. Okay, that's where we left. So that gives us phi dot. So what is phi dot? Well, that means phi dot is d phi d tau. It's approximately that. Okay, then d phi dr becomes d phi d tau times d tau dr is approximately this. Remember, d tau dr was this object here, square root m on square root 2 times the square root of the energy minus the effective potential. Okay, now we have this bit in front, which is the d phi d tau. Okay, so we have d phi dr, and that suggests that we should be able to integrate this to come up with a term phi as a function of r. Well, we should be able to, but in reality, there's no exact analytical solution to it, so we're going to have to resort to numerical integration. Okay, so we now have d phi dr is approximately this, and we substitute in 2h in terms of the variable r. What we'd like to do, though, is in the Mathematica notebook, we're going to find the reciprocal of r. R is 1 on u, and make a substitution, replace these with u's, which will make our, it helps with the integration. It integrates more easily if we take 1 on r to be u, that integrates more easily than having a 1 on r, because it gets tricky around 0 and elsewhere. So we make the substitution r is 1 on u, which implies that the r to u is minus 1 on u squared. And that gives us d phi du is approximately this object here when we substitute in. And don't worry about that, because that minus u squared out the front here is going to multiply through here, and it's going to remove this 1 on u squared bit, which makes integration a little bit tricky. And what it gives us when we do that is we're now going to have our minus plus. We're going to have square root 2m. All right, square root 2m, square root of this object here. Now, this becomes a squared u squared. The 1 on u squared, which might have given us trouble during integration, now disappears and just becomes a 1. All right, and then here this u becomes u cubed. Okay, so it's looking all right now so far. I can say that because I know I've used it in the Mathematica notebook and it works. All right, so the effective potential in this new variable becomes this object here. And that is what we'll put in the Mathematica notebook, and that's what's taken me all this time to get here, because I need to justify this, why I'm using this. Now this leads, so we're after the integral numerical integral of this object here from some u1 to u2. Remember, u1 is 1 over r1, r1 is some distance out, and u2 is 1 over r2. r2 is some distance to which we want to integrate. Distance from the outer event horizon. Okay, so now we numerically integrate to find the relationship between the coordinate angle phi and the radial coordinate r. Okay, actually when I say r1, it is from the center of the black hole out. Okay, we're just going to be interested in that regions from r1 is far out to r2 is the event horizon itself. Okay. All right, now there exists a good program for carrying out this integration using a Mathematica program that can be found on the website that accompanies James B. Hartle's textbook, which is a very good textbook, Gravity and Introduction to Einstein's General Relativity. Now, other versions can also be found on the web, but I've provided a link at the beginning here, which shows you where you can find these Mathematica notebooks. You'll need the Mathematica program to run it. All right, so here's an example using it. Okay, so an example of a bound orbit. I'm going to be focusing on using this notebook in the next video, so I'll give you only a brief look at it this time, and then I'll make this the subject of the next video, but can I just give you some idea of what it can do? So a bound orbit, set the angular momentum 4.65 units. Remember, we've got the mass of the black hole set to 1, we have the mass of the test particle set to 1, okay, or the mass m is set to 1, g is set to 1, c is set to 1, okay, and so we're really doing the angular momentum per unit of mass. Set the energy to slightly negative. We'll set a starting distance of 40 units out, which is 40 gm on c squared, okay, out here somewhere, 40 gm on c squared, so Schwarzschild radius is 2 gm on c squared, so 40, you can imagine 20 times that distance out. And now 2 gm on c squared actually corresponds with the stationary limit surface of a Kerr black hole. The actual outer event horizon of the Kerr black hole is actually about 1.6 gm on c squared, a bit less. All right, so let me just show you briefly. Okay, just be patient while this program opens. I'm only going to show this briefly too. I'll make this a subject in the next video. So the program is actually written for the Schwarzschild geometry, okay, and we have to change a few things. Now, I've added these units, C is 1, G, and so on, because in the next video I'd like to change these to their actual units and run the same program as well. Okay, now the stationary limit surface for a Kerr black hole is 2 gm on c squared, but the outer event horizon, gm on c squared plus square root of this, gm on c squared squared minus a squared. A is the angular momentum or per unit mass or the spin parameter of the black hole. Okay, so, and that event horizon is about 1.67 gm on c squared units. Okay, so here is now the effective potential that I was talking about earlier. Here we are. In this case, G, M, little m, and C, and so on, they're not going to appear because they're being set to 1 above. Let's pick the angular momentum, 4.65, and then plot the effective potential. Okay, and here we get this, okay. The derivative to analyze the turning points, here and here, analyze and turning points. Here they are. Okay, so in this particular example, I've set the energy to plus 0.305. Okay, and that's slightly above the maximum of the effective potential. Just here, that's the orange line here. Okay, next thing, there's some turning points there. This is analyze motion. We start the particle off at 50 units. Yeah, an orbit here, this for bound orbits, you might want to specify how many times you want to plot the orbit. You could have 1 orbit, 2 orbits, and 3 orbits, and so on. This is an error thing. Because we're doing numerical integration, we have to be careful around turning points. The integrand here can diverge quite a bit. So it was actually set at 10 to the minus 8, but me being over enthusiastic, I've set it at 10, 1 part in a billion. Anyway, it still works. I'm hoping it works better. But anyway, here we go. Tests for different orbits. you can see what I've got at the moment. This test tells me I've got a plunge orbit. So coming from far away from the mass, from the source mass, and heading into the source mass and ending there. So it's a plunge orbit. The test for that is that the energy parameter is set greater than the maximum effective potential. Okay, in we go. Okay, integrate this, then we have a look at number of orbits around it goes. Okay, so the Z parameter varies according to the number of orbits. And don't forget, and the other alteration we had to make as well. Oh, I changed some of these. Also, I changed this U2 so that it ended up at being at the event horizon. So that remember how we found it was about 1.67 or something like that, 1.6 or something. So I changed this. It was 0.5 before, which was fine for the Schwarzschild geometry because 0.5 reciprocal of that is 2 GM on C squared is the outer event horizon. But for the Kerr geometry, the outer event horizon occurs further inside. Okay, so I've changed that 0.67 here, just as approximation, 0.67. Where else? Did I change anywhere else? Okay, so just be aware that needed to change as well. Okay, there's our effective potential there in the integration variable W, which will then be analysed between U1 and U, however close you want U to be. Okay, now don't forget, we're not dealing with a sphere here, spherical coordinates. We're dealing with spheroidal coordinates. And so you're going to need the R squared plus A squared term here, then the cos of the angle, okay, the sine of the angle. This is a parametric plot, and this will give us the plot in the equatorial plane looking down from above, from the positive Z direction downwards. Okay, so we end up with this. I've added some features here, axis style, black thin, they're all preference things, plot range. Each of these plots vary in the region covered. Okay, I've added a disk here. This disk here is the RU is the outer event horizon distance, and I've accentuated the outer event horizon by putting in edge form directive, that thick blue line. Here is the event horizon, don't miss it. The disk is centered on the origin, as it should be, because we have our black hole centered on the origin. And we're plotting over 2 pi, we want the whole circle. And then when we put both together, that's this plot and this plot together, what we get is our particle of mass m coming from far out here, 50 GM on C squared out here, and orbiting, coming here on a plunge orbit, going in, and eventually crossing the event horizon. Okay, that's what we have. All right, now I think that'll do that. All right, now quit that. What else can we do? Let me just show you a couple other things. All right, here's another example of a bound orbit. Angular momentum 4.65 units per unit mass. E is minus energy is set here, so the orange line is where E is set, the energy parameter. Bound orbits occur when E is less than 0. Here we go, and we're starting way out here, and in we come. Here we go, with this one around there. All right, we can get all kinds of interesting orbits. Can I just go back here? That was one orbit. This is 2 orbits. Same thing continued for another orbit, and continued for a 3rd orbit. There we go. All right, keep going. Now here's an example of a scattering orbit, beginning far off and ending far off. Again, H is 4.65. Change the energy parameter. E is plus 0.1. That one there. Okay, like that. So for scattering orbits, E is greater than 0, but E is less than V max, so it's less than the turning point here. And we have this scattering orbit like this. Okay, and I think there's one more to show you. An example of a fallback orbit. So here's a particle emitted. So you can imagine a spaceship crossing an event horizon. Before it crosses the event horizon, it emits some particles, but those particles, unfortunately for them, they fall back onto the event horizon. You can see here, actually emitted out here, and they fall back on. Okay, so must have E less than V max for that. So you could have it anywhere, anything below. It's got to be less than V max. And there you get a fallback orbit where it begins near the event horizon, doesn't have enough energy to escape, and falls back in. Okay, is that it? Another plunge orbit, 4.65. this time 4.65 plus 0.305 up here. Okay, and as we go, plunge orbit coming in again like that. I don't know if I have one more. Here I go. Now this one starts further in, much closer in at 6 GM on C squared. It even starts with higher angular momentum, 6.5 instead of 4.65. The energy is set to 0.915, and again, we still have a plunge orbit. In it goes. I like these plunge orbits. Okay, so the mass starts closer in and with higher angular momentum, but it still ends up in a plunge orbit. Okay, and that's it.